Hello, in this video I am going to introduce you to reactions involving aldehydes and ketones, where I am assuming that the R group is an alkyl group containing a carbon, that is a carbon skeleton. So the focus is going to be on the carbonyl carbon, that is this carbon here. We are going to use that carbonyl carbon as an electrophile, so that when we have a nucleophile, we expect the nucleophile to attack the carbonyl carbon and open up that pi bond. Okay, so the question is, why would that carbonyl carbon act as an electrophile? Let's think about it. Between a carbon atom and an oxygen atom, which one is more electronegative? Of course, it is oxygen. It's more to the right on the periodic table. They are on the same period, but oxygen is more to the right. So they do not share electrons equally. The electrons reside more on the oxygen atom. And we can actually draw a resonance structure where the electrons are on the oxygen atom, leaving a carbon atom with an empty orbital. And that is why the nucleophile can actually attack that carbonyl carbon. Alright? So, which kind of nucleophiles can we use? We can use oxygen nucleophiles like water and alcohols. We can use sulfur nucleophiles, nitrogen nucleophiles, hydrogen nucleophiles, and carbon nucleophiles. We can group them in that format. In fact, we have used some of these. For example, we have used lithium aluminum hydride and even sodium borohydride and Grignard reagent to attack carbonyls under the preparation of alcohols by reduction. We can also utilize cyanide to attack the carbonyl, and we can also do what is called a Wittich reaction, which we are going to discuss later. In this video, our focus is going to be on the oxygen and sulfur nucleophiles. We can utilize water as a nucleophile to attack the carbonyl carbon, and that leads to the formation of hydrates. Okay? What you notice here is that the reaction is forward favored when the carbonyl carbon is more electrophilic. So if we attach it to the fluoride groups, then we know that fluorine is more electronegative. So it's going to remove the electrons. It's going to have the electron residing more to itself than on the carbonyl carbon. So it becomes more, the carbonyl carbon becomes more electropositive. It becomes more electrophilic. Okay. While if we do have the alkyl groups, the alkyl groups are known to be electron donating. So therefore, this one is not as electrophilic as the one here, or as the one that contains the hydrogen atoms. So the reaction in the case of acetone is actually reverse favored, while in these cases these are forward favored. Let us look at the mechanism of hydration. It could be base catalyzed. If we use a strong base, the strong base is going to do a nucleophilic attack followed by proton transfer to form the hydrate. If we use a weak base or a weak nucleophile, then we need the help of an acid. What are the examples of weak bases or weak nucleophiles that you know? Well, if you use water, just water on its own, then we will need the help of an acid. So H2O in the presence of sulfuric acid, which will be able to form the protonated water. And then we can utilize the lone pairs on the oxygen to do proton transfer, and we generate this structure here, which is the protonated oxygen of the carbonyl. Now, we can draw a resonance structure for this compound to demonstrate why it's now easy for the carbonyl carbon to be attacked. Okay, so this carbonyl carbon becomes more electrophilic if we protonate the carbonyl. This electron could go there, and then we end up with that resonance structure. Okay, so therefore, in the next step, we are going to utilize we're actually going to utilize the protonated carbonyl oxygen and have water do the attack. So water, which we said is a weak nucleophile, now it is able to attack that carbonyl carbon because it's more electrophilic, and we end up with 1, 2. So we have water, we have the hydrogen, and we have oxygen attached to that. And this water here is going to be protonated. So we have that. So we need to do deprotonation in the next step, where we are going to use water to do the deprotonation. That goes there, and we end up with 1, 2, that is hydrogen, OH, OH. So we end up with the hydrate. Okay, so whenever we have a weak nucleophile, then we need to use an acid catalysis. Next, let us look at alcohols as oxygen nucleophiles. We know that alcohols are weak nucleophiles, so under acidic conditions, we can use the alcohols to attack the carbonyl, and that forms what is called an acetal. Okay, acetals are product favored if we use a carbonyl carbon that is more electrophilic. Otherwise, if we use one that's less electrophilic, like we know that the alkyl groups are electron donating. So this carbonyl carbon here is not going to be as electrophilic as the first one. So therefore, this reaction is reverse favored. But we can make the reaction to go forward if we remove part of the product that is being formed. Like by removing water, the reaction can be forward favored. If we use a diol, the second diol is going to come in and do another attack, and we end up with what is called cyclic acetal. And of course, the 5 and 6 membered rings are stable. So therefore, we can form cyclic acetals if we use a diol. Now, let us look at the mechanism of the acetal formation. So in the first step, we say that these are weak nucleophiles, so we need to first of all do protonation of the carbonyl. So in the first step, we do a proton transfer, and then after we do a proton transfer, now we can have a nucleophilic attack. Once you have the nucleophilic attack, the alcohol that we are using here is going to be protonated. So then we need to do deprotonation. So proton transfer to do deprotonation, and then we have installed the first ethoxy group. And that is called hemiacetal. In the next step, remember the key thing is we want to install an ethoxy group in this position so that we can form an acetal. So in the next step, we need to do proton transfer to turn the hydroxyl group into a good leaving group. So we do proton transfer, then after that, we do a loss of leaving group. So loss of leaving group, now transforms this one into a good electrophile. So we do nucleophilic attack. That's going to protonate the alcohol, so we do deprotonation, proton transfer, to generate this stuff, which is going to be our acetal. Now, cyclic acetals have some utility in terms of being used as protecting groups. Okay, so we can protect a ketone or an aldehyde with cyclic acetal. When we use a diol, then we end up with a cyclic acetal. So that protects that group. Let us look at an example that we can use in this case. Assuming we wanted to do reduction, where we want only to reduce the ester group into an alcohol. So this would require lithium aluminum hydride. And then in the second step, we would need water. But if we do that, the problem is it's going to reduce this also to an alcohol. So there's something else we need to do before we do that reduction. We can protect this group. So in the first step, what we do is we can use a diol. In the presence of sulfuric acid, and that is going to protect the ketone. Leaving us with the ester. So the diol does not protect esters, it only protects ketones and aldehydes. So then in the next step, we can do our reduction. Lithium, aluminum hydride, and then we use water, and that ends up giving us the product that we expected, but still with the carbonyl being attached to the cyclic stuff. Then we can do deprotection. Deprotection requires the use of an acid. So in the first case, we are removing water. Remember we said we can favor this reaction if we remove water. But if we do this again under acidic conditions, in the presence of water, so instead we are adding water instead of removing water, then we end up with that product. Okay. Another way you could do this is, instead of doing that, you can just say, after lithium aluminum hydride, you can just say you're utilizing sulfuric acid in the next step in the presence of water, and that will go directly to form the product, because it will be a source of proton here, and it will also be able to directly deprotect the carbonyl. Sulfur nucleophiles also react in the same format like alcohols and diols. For example, a thiol will form thioacetal, a dithiol will form cyclic thioacetal. Cyclic thioacetals can also be used as protecting groups. Okay, so when we use it to form a protecting group for either a ketone or an aldehyde, then we're going to end up with this cyclic thioacetal. We can transform cyclic thioacetal directly into an alkane by doing a reduction using Rennie nickel catalyst. So this is another cool way to transform a carbonyl into an alkane. Remember the one we discussed earlier under Friedel-Crafts acylation? That was called Clemmensen reduction. Now we have another cool way to do that, okay? And of course, there's another method that we're going to discuss later in this chapter, which is called Wolff-Kishner reduction. Thank you for watching and have a good one.